Hey everyone, and welcome. Today, we are jumping headfirst into Google's brand new Gemma 4 family of AI models. If you're at all curious about what's just around the corner in artificial intelligence, you have come to the exact right place. So let's just start with the big question, the one that probably keeps AI researchers up at night. It's this huge challenge, right? How do you make an AI more intelligent, make it respond in a split second, and shrink it down so it can actually run on something like your phone? I mean, it really feels like you should have to pick maybe one or two of those, but not all three. Well, that's where Gemma 4 comes in. This is Google's answer to that very puzzle. And it's not just one model, it's a whole family of them, each one designed to solve this problem in a slightly different way. They're built to be incredibly versatile. We're talking everything from tiny tasks on your device to some serious heavy lifting in the cloud. Okay, so let's properly meet the family. The whole idea here is choice. There really is no one-size-fits-all solution in the world of AI, so Gemma 4 gives you a model for just about any task you can dream up. Now this really lays out the entire strategy. You've got the heavyweight champion, the 31B, which is this super powerful, dense model. And that just means all of its brain power is used for every single task. Then you've got this incredibly efficient 26B A4B model, which uses a really cool approach we're going to unpack in a bit. And finally, you have the E4B and E2B models, which are designed to be small and fast enough to live right on your phone. And here's the kicker. They're all multimodal. They get text, they get images, and those smaller models can even process audio. So, next up, let's talk about how these models think efficiently. Just imagine an AI trying to read a huge book or follow a really long conversation. If it has to go back and reread everything from the very beginning for every single new word, it just becomes painfully slow. This is one of the core challenges in AI, handling long-term context. And this slide just illustrates the two main ways to do it perfectly. On one hand, you've got global attention. Think of it like having a complete word-for-word transcript of a meeting. It has perfect memory, but man, is it slow and resource-heavy. On the other hand, you've got local attention. This is more like only remembering the last few sentences someone said. It's super fast, super efficient, but you run the risk of totally losing the bigger picture. So the problem with only using that fast, local approach is captured perfectly by this quote from the source material. It's like a game of telephone. The information gets a little bit twisted and diluted every time it passes through another layer of the model. So to fix this, Gemma 4 does something really smart. It interleaves both types. It gets the speed of local attention without losing the perfect memory of global attention. So how does Gemma 4 make those powerful but slow global layers faster? Well, it has this awesome playbook of tricks. First, it groups its queries together, which drastically reduces memory. Then, inside the AI's brain, there are these things called keys and values. And by simply making them equal, it slashes the memory needed for its cache right in half. And finally, it uses a technique called P-rope to very cleverly add positional info, like where a word is in a sentence, way more efficiently. It's all about making these small surgical tweaks to get huge gains in speed. So we've covered how it thinks, but what about how it sees and hears? This is where we get into true multimodality, and it all starts with giving the AI a pair of eyes. The technology that makes this happen is called the Vision Transformer, or VIT, and the concept is it's genius. It basically treats an image like it's a sentence. It just chops the picture up into a grid of tiny little 16 by 16 pixel patches, and then it reads them in order just like they were words. But that brings up a pretty obvious problem, doesn't it? I mean, how many photos on your phone are perfect squares? Almost none of them. So how does a system that's built on a perfect grid handle all the weird shapes and sizes of real-world images? The solution is just as elegant. Gemma 4 adaptively resizes and adds padding to the image so it fits the grid, but it does it while keeping the original aspect ratio. Then, and this is the clever part, it gives each little patch a 2D positional code. It's basically telling the AI, hey, this little square came from this exact X and Y coordinate on the original picture. It's a map that lets the AI perfectly reconstruct the image in its mind. And what about hearing? Well, for the smaller models, it's this fascinating three-step dance. First, they take the raw audio and turn it into a visual map of all the frequencies. That's called a spectrogram. Then, they turn that map into a sequence of what are called soft tokens. You can think of these as the audio version of those little image patches we just talked about. And finally, a specialized AI component called a conformer, which is amazing at understanding sequences, processes those tokens into a language that the main model can finally understand.
All right, we've seen all the features they share. Now, let's get to the fun part and unpack the special magic that makes each model in this family so unique.
First up is the mixture of experts, or MO, which is the engine inside that 26B model. And this analogy is just perfect. Instead of having one giant general-purpose brain do all the work, Mo has a smart router that sends your request to a small team of specialists. This is the absolute key to getting massive performance without that massive slowdown. And this slide explains that kind of weird model name, 26B A4B. It has 26 billion total parameters. Those are the sparse ones. Think of it like every single doctor in an entire hospital system. But for any one question you ask it, it only activates 4 billion of them. Those are the active parameters. Those are the few specialists you actually talk to for your appointment. That's how a 26 billion parameter model can run almost as fast as a 4 billion parameter one. It's just brilliant. Now, for the smaller on-device models, their secret weapon is something called per-layer embeddings, or PLE. And honestly, the best way to think about this is that it gives the AI a custom-made cheat sheet for every single step in its thinking process. At each layer, it gets this little boost of extra information, which makes it perform like it's a much, much bigger model. So that's what the E for effective in their names is all about. The small model's core brain, its total parameters, is what has to run in your phone's super precious, super fast RAM. But that little model can also access a massive cheat sheet, that lookup table, which is stored in slower flash memory. This gives a model with only about 0.8 billion active parameters, the effective power of a 2 billion parameter model. It's an incredibly clever way to get huge performance out of a tiny package. Okay, shoo. I know that was a lot of technical detail. So let's zoom out, let's bring it all together, and talk about why these innovations really matter for you, for developers, and for the future of AI. So here are the big takeaways. This means we're going to get smarter, more powerful apps that can run right on our phones without even needing an internet connection. It means developers get the flexibility to pick the absolute perfect tool for whatever they're building. It unlocks brand new experiences with AI that can see, hear, and read all at once. And this is a big one. It makes powerful AI more efficient, which means less energy use and lower costs for everyone. So I'll leave you with this one final thought to chew on. We're watching AI get way more powerful and way more compact at the exact same time. The question isn't really if it's going to be everywhere anymore, but where we're going to see it pop up next. What happens when this level of intelligence is built into our cars, our glasses, our homes? The possibilities are, well, they're pretty fascinating to think about.